G'day. Today I thought we'd have a look at an inexpensive Chinese condenser microphone with a view to adjusting the bias on the input FET. This is branded as MC01, but you'll find the circuit of this one is very similar to the MXL V67G or the MXL 2001. Basically, there are two styles, two popular designs of these large diaphragm condenser microphones coming out of China. There's the one with the solid state output, the kind of SCRPS related circuit, and there's this one which has a output transformer, which the circuit is, the front end is curiously reminiscent of a Neumann U87, and what's different is having the output driven by an emitter follower, and the output transformer ratio being much lower, about 2:1. And that's kind of reminiscent of at least one incarnation of the AKG C414. So they're copying from the best, at least. You'll notice we've already made a change to this one. You'll see this resistor here is not a resistor at all. This is an unusual little device. As you can see, that's in a TO92 package, but with only two legs. That is a J508 constant current diode. Now let me explain what's going on there. So what we've done is we've already replaced R10 in the emitter follower here with that constant current diode. And what that does is that reduces the distortion coming from the emitter follower stage. That brings the gain of the emitter follower much closer to unity. And it also means that the current through that leg doesn't depend on the DC offset of that voltage, and that's helpful because the other thing we've done is we've tacked in an extra resistor across here in order that the base of that transistor be biased by a voltage divider rather than simply through that resistor there. That modification gave us about 4 dB of extra headroom, and was well worth doing. What we're going to look at today, though, is the biasing of the FET. Now, I'm going to look at how this circuit really works. So, the quiescent current through the FET is determined by the voltage offset between gate and source. And in this circuit, that's brought about by these two resistors here. Now, this transistor here is an N-channel junction FET, and if the gate was pulled down to the same voltage as the source, then the maximum current would be flowing through the channel there. That would be the saturation current, or IDSS, current between drain and source at saturation, would be allowed to flow through there. If the voltage on the gate is brought sufficiently negative with respect to the source, then the FET will eventually go into pinch off, where effectively no current will flow. And the whole thing is all about the voltage from the capsule modulating that gate voltage around about that point and giving us a change in the amount of current flowing through there. So how does this work? How do these resistors in the source leg somehow bring the gate to a lower voltage than the source? How does that work? And it seems odd because there's a huge resistor here, there's 1 gig, and we've got, 1.8k, 3.9k. How's this all working? Well, of course, there is no current flowing through this. And so this, it's effectively at ground. Whereas with a quiescent current that's flowing through the FET, voltage drop across these means that the source is more positive than the gate. Or, look at it another way, the gate is negative relative to the source. See, what they've done is they've put this capacitor here across one of these source resistors, but not the other. Now, what's that all about? Okay. So, this is all about source degeneration. This is a kind of negative feedback that occurs if we just have a resistor in here. Because, if you think about it, that voltage offset between gate and source is set by the voltage drop across these resistors, and that's determined by the amount of current flowing. But of course, the whole point of the exercise, how we reproduce a signal, is by modulating the amount of current flowing through there. And that means that the voltage drop must be changing as well. And it turns out that what you effectively get is a kind of negative feedback. It linearizes the behavior of the FET. However, what you're doing is you're trading gain for lower distortion. So if you didn't have a capacitor there at all, then you would get the maximum amount of input degeneration, whereby some of the changes in output current would be inducing a change in the voltage drop across these resistors, which would change the voltage between source and gate. So what they've done is that they've taken the source resistor and they've split it between two, and they've stuck a capacitor across one, so that bypassing that source resistor, what that does is that means that the source resistor there is contributing to the DC bias conditions. But it means that when the current through here is modulated by the signal, that has no effect, because the capacitor just passes the AC component. So effectively, from an AC point of view, it's as if we've got 3.9k of source resistance, whereas from a DC perspective, it's like we have the sum of those two. Now, the plan is to replace one of these resistors with a trimpot, and then experiment in changing the value of that and seeing how that makes things behave. Now, I'm thinking that it might be best actually to adjust R7. The reason being that if you change this one here, you're not just changing the biasing of the FET, you're also changing the amount of input degeneration you're getting. So, quite difficult to tell exactly of the effects that you note from that, what they're caused by. So, I think the best strategy is to find R7, to replace it with an appropriate trimpot, and then we'll inject a signal here, and we'll have a look at the output as we change the value of that bias resistor there. Okay, so let's just find R7 on the board, and I think that's there. Quite a bit pointed than that. That's a bit blunt, isn't it? There we go. I think it's that one there. Let's have a little look. Need to make sure that we're talking about the same resistor, of course. Let's see, brown, grey, black, brown, 1800, 1.8k. Great. Okay, we'll just take the screws out of that board and set those aside. See how much slack we've got. I think we might just, yeah, don't like to stretch those wires too much. You end up having to fix all the ones you've broken off, so I think we'll just set them out like that. That should do the trick. I'm sure I'll try and do this on camera, to be honest. I have to watch me burn myself. Oh, that's one leg out. There we go. There's R7. Okay, let's just have a look and see how those pads are looking. Okay. They look fine. I haven't lifted any traces yet, but the night is young. Let's just get in there with a bit of wick. Also wick. And clean those up. Let's have a little look at that. Yep, that looks pretty good. Just have a look, see whether we can see daylight through those. Well, one of them we can. The other one not. Okay. Have another go at that. See how we went there. Looks pretty from there. And that looks clear. Excellent. So there we go. Now, hunt around for an appropriately sized trim pot. Okay, so what we found are some 10K trim pots. Now, this is going to be a little bit tricky because we actually want to put that between the wiper and one of the outside legs, so we're going to have to bend it, which is pretty annoying. And last time I did this, the only way I could get it to work was to actually cut off one of the legs, which is a shame because ruining a perfectly good trim pot, but there you go. Okay. Now, before I pop them in there, what I might do is preset that trim pot so that it's at 1.8K. I think that would be good. Okay, there we go. Just power up the meter. Okay, and we'll go into ohms. Connect up our trim pot. Okay, and it's pretty much exactly 5K. Now we seem to be dead center, which is nice. Okay, so I just want to preset that. Which way are we going? Down? We are. Okay. Okay. Near enough. 1.8K. Okay. Well, it's not high art, but it'll do. So what we have now is basically we've replaced R7 with that trimmer, currently set to the same value that R7 was before we started. And what we should be able to do is apply signal to the input, connect this up to a preamp, monitor the output, and we should be able to adjust that trimpot in order to optimize the bias according to whatever conditions we might be looking at. Now that might be distortion, and it might also be in terms of headroom. Kind of two different approaches you can take there, and probably two different optimum bias points. So what we'll do is we'll set up the preamp and we'll set up our test. Okay, so we're starting to set up our test rig. What I've got is I have an M-Audio DMP3 dual mic preamp, which is phantom powering this microphone. And what we're going to do, I think, is we'll start out by checking the headroom, in which case we'll be applying an audio signal from generator up here, because that has a good fine control of the output level, and we'll just eyeball the amplitude on the scope here, and we'll find an optimum level there, and then we'll fire up the dynamic signal analyzer and we'll have a look at the harmonics, and we'll see if we can find an optimum bias level from the point of view of harmonic distortion, and then maybe we'll see how much they differ by and possibly find a compromise point between the two. Okay, this is the signal generator we're using as a source, and so we're set to 1 kilohertz sine wave, and our output level is about -10 dB. So what we've done, we're applying the signal here at the point where the capsule wire joins the board, between there and ground. Now, if we have a look at the scope, we've got the preamp gain set to minimum, currently 2 volts per division. So we're seeing our output here. Now, if we bring the level of that up a bit in 1 dB steps, it's still looking... okay. Alright. It's about -4 dBV. Okay. So have a little go at that trimmer and see if we can get it to not clip on the bottom like that. Oh, that's worse. And it's kind of worse as well. Okay, I'll go this way. Oh no, that's better. Oh. Okay, there we go. Alright, let's go up another dB. Okay, yeah. Let's keep going. That looks good. I might have to... Oh, wrong way. Go to 5 volts per division. And go to -2. That's 1. Okay, no, it's still squaring off on the bottom. Okay, that looks good. Oh, that's going. Oh, here we go. Now the top's going. Okay, that's good. It's a little bit on the bottom, a little bit on the top. What we might do is just. There we go. So that's about 10 dB up on where we started. Suggest we just try and even that out. And we'll come back a dB. That looks good. Back 2. Looks lovely. Back to 2 volts per division. That's too much. Can't really look at it like that. And unfortunately, our preamp gain doesn't go any lower. So, okay. Well, anyway, that looks good. So that's our bias optimized for headroom. And you can see the default value was quite a ways off because the clipping was asymmetric. It was on the bottom. So that's actually quite reasonable. And we'll go back to 5 volts per division. There we go. And yeah. So that's at -2 dBV or thereabouts, which for a microphone level signal is rather a lot. Okay. We'll just fire up the analyzer. Pardon the noise. Okay. Power spectrum linear resolution, yeah, that's good. Let's go in frequency mode. We'll set we'll go 0 start, I suppose. Set a frequency span of 20 kilohertz. That'll do. And we might as well set a start frequency of 20 hertz just for the sake of completeness. Okay, now what we need to do is we need to set our source. So source, and we want fixed sine, and we want 1 kilohertz. We want the source level to be, I don't know, 100 millivolts. Reasonable. Okay. That's not too bad. No sense in looking at the whole spectrum, really. Just need to look at the first few harmonics, so let's go back to setting up the frequency span. Let's give it maybe 8 kilohertz. Just spread that out a little bit. That's a bit better. I might actually go with 0 start. It's just a bit easier to read if we go that way. That's better. Okay, so there's a fundamental, and there's our second harmonic. That's looking pretty clean, isn't it? Okay, I might drive that a little harder, I think. So we'll go back to the source, and we've got source level, and we might go 500 millivolts peak to peak. Okay. more second than third. So we're probably not clipping. Perhaps we'll do that. We'll just keep going higher till we see it clip, and then we'll know we've overdone it. Let's go 1 volt. Yeah, that's starting to look bad. What if it was... Rah. Okay, that's definitely clipping. Look at this. We've got third way up above second, and there's a lot of it. Okay, let's go back. Source level. Let's try 1 volt. Is that acceptable? What I might do, I can actually, there you go, view input. Let me just input versus time on 1. Yep, that's clean. Okay, that looks good. Measurement display is power spectrum again. Thank you. All right. Okay. Now we want to see our distortion. So go our markers. Look at harmonics. We want to calculate THD. Fundamental frequency is 1 kilohertz. Okay. There we go. We've got markers on all the harmonics, and we've got THD at minus 41 dB. Okay. Now, let's see if we can do better than that. Let's see if we can, by turning this trimpot, we can improve that at all. That's worse. 41, 42, 43, 44, yeah. I see the seconds dropping. Look at the way that second harmonic's dropping away. 47, that's looking really clean. Oops. So it just fell off there. Oh, yes. That's our signal. That'll definitely cause problems. There we go. Okay, minus 46. That's worse again. Go this way. I was watching this second harmonic here. Oops, don't scratch your analyzer screen. That's pretty amazing. Okay, so what we can do, we can change that axis display. Scale, we can go with, let's try y-axis auto scaling. Oh, that's good. That's good. Okay. Well, we're not going to get that much lower. What we can do is do a little bit of averaging. We can maybe average, I don't know, 8. Okay. Well, what? This catches me out. The unit is calibrating again as it warms up. So Just wait for that. And there we go, we're live again. Okay. Ooh, yeah. I'm fiddling with that, didn't I? Oh, it doesn't seem to be changing, and it wasn't. Now, I might actually turn averaging off again. It's just a little bit easier when adjusting the trimmer to be careful what you touch. Well, that's going up again. Look, that's pretty good. So we've got our second harmonic quite a ways down. 12.5 dB per division. That's the reason why I don't like auto scaling. Alright, that's what we'll do. Here we go. So that's at 14.7. Look at that. I'll write that down. So the fundamental is a plus 14.7 dB. And, well, zip across to the second harmonic over here. Come on. There's probably a way you can do that more precisely. There we go. And that is at minus 52. So that is our best adjustment of the bias resistor in terms of distortion, and that brings our total harmonic distortion at 1 volt peak to peak input to minus 47 dB. You can work that out as a percentage if you feel like doing the math. I will do that a little bit later. Okay. I guess having found the optimum point for distortion, it would be worth checking what our headroom was. So we might actually switch back to the other test. Actually, we might be able to just do that with this. Let's try that. So let's do the view input versus time on channel 1. There it is, lovely. Okay. And if we then go to the source, there's a button for that. Yeah. Source level. We go to 2 volts peak to peak. That's quite symmetrically clipped actually. It's not bad. Not bad at all. Let's go to 1.4 volts. Okay. So we can see it's not quite as good from a headroom point of view, because obviously it's clipping there more than there. It's clipping at the top of the waveform first, but in so doing we've brought our distortion down as low as we can get it. Well, I feel that in terms of headroom, that's still very good, and I think I would like to keep that at a point where it's optimized for distortion. So I think I'll go with that. So all that remains to be done now is to remove our trim pot and find out what resistance value it actually has. That's that out. Should be relatively easy to get the other leg out now. There we go. Connect up our trimmer and see what we've got. And there we go, 753 ohms. Okay, so I've dug up a 750 ohm resistor and popped it in place of that trimpot, and just fired up the analyzer one last time just to make sure that it's performing as it should. So this is with 1 volt peak to peak input, and that's our second harmonic all the way down there. So there you go, that's how to set the bias on an inexpensive Chinese condenser microphone. As you can see, the value it came with of 1.8K was quite some way away from the 750 ohms that was optimal. And hope you enjoyed it. Thanks for watching.